Math 111. Today we're going to talk about section 5.7, in particular the difference of squares pattern of factoring. We're going to be talking about another type of factoring, another tool we can use in our factoring toolbox. I'm going to write down a couple of binomials. And let's say I ask you to multiply these two binomials. Alright, the binomial is, first one is a plus b times the second one a minus b. These are what they call conjugate binomials. By that, I mean the sign in between the two terms is opposite. They are not negatives of each other. Alright, the negative of a plus b would be negative a, negative b, right? But conjugate, all that means is the sign in between is different. Right, so it's a plus b times a minus b. Now if I ask you to multiply these two binomials, if I FOIL these two binomials, I'll get a squared for the first product minus ab, well, b times a is equivalent to a times b, so I'll call that minus ab is the outer product, plus ab would be the inner product, keeping the variable products in alphabetical order, as is the custom, and minus b squared would be the last product. And when we go ahead to combine the like terms, we'll see minus AB and plus AB are like terms, can be combined, and they are indeed opposite terms. So when I clean this up to get a final response, I get a squared minus b squared. I call this a difference of squares pattern. And I'm sure you're familiar with this from your first course in algebra. Difference of squares. Well, the idea here is when I multiply conjugate binomials, I will always end up with what I call a difference of squares pattern. I call difference of squares for obvious reasons. In this case, it's a squared minus b squared, the difference of the square in b and the square in a, right? Well, so if I ask you to factor this difference of squares binomial, well, from our above example, we know that it came from a product of those two conjugate binomials. So the real value of this is if I can recognize a difference of squares pattern in the binomial I'm given, I can instantly write down a factored response basically by inspection if I know the difference of squares pattern. Alright, we played this game before, I'm sure. So let's jump right into some examples. If I ask you to factor x squared minus 4, well, x squared minus 4 is, of course, I can write as x squared minus 2 squared. And of course, from that difference of squares pattern, it's then equivalent to the product x plus 2 times x minus 2. And that would be my completely factored response. And up the ladder we go here. If I ask you to factor this binomial, well, I think we can recognize this as a difference of squares pattern without too much arguing. 49 is a square. It's a perfect square of 7. X squared is, of course, the square of x, and 16 is, of course, the square of 4. So I can rewrite this as 7x squared minus 4 squared. Most times we don't have to write that intermediate step. Most times we can go right from here to here. 7x plus 4 times 7x minus 4. And indeed, if you multiply this product, you will indeed get 49x squared minus 16. Okay, try another one. Factor 81 p squared minus 25. Well, similarly, 81 is a square, p squared is a square, and 25 is a square. Let me try to do this one just by inspection. Well, this will work if I have 9p in the first slots, 5s in the last slots, and plus here and minus here. 9p plus 5, times 9p minus 5. Notice, multiplication is commutative. So I could have easily reordered those factors in my response and gotten this equivalent answer, 9p minus 5 times 9p plus 5. Anytime you're multiplying expressions in your final answer, those answers are unique, at least up to the reordering of the individual factors. Multiplication is commutative. Multiplication is, of course, associative also. Try another one. Factor 64a to the fourth minus 25b squared. Well, I know what you're saying here. I thought this was a difference of squares topic we're talking about. Well, of course, a fourth power can also be seen as a square. Really, it's the a to the fourth power. I could look at that as a squared squared, could we not? Let me show you where we're getting at here. I can rewrite 64a to the fourth equivalently as a squared squared, could I not? And 25b squared I could rewrite as the square of 5b. And of course, once I establish I've got a difference of squares, I could call this then 8a squared plus 5b times 8a squared minus 5b. And neither of those resulting factors are factorable. Can't factor further. So these are both prime. So I call this my completely factored answer. Okay? So you can even play this game with powers higher than 2. Let's try another one. Factor x to the fourth minus 1. Alright, well, a little bit of a trick here. Let me show you where we're headed. If we have x to the fourth minus 1, well, 1 to any power is 1. So what I can do is take that x to the fourth and rewrite that as x squared squared. And of course, 1 is equivalent to 1 squared. Now, why do I write it in that convoluted form? Well, the idea here is I can easily recognize a difference of squares pattern. I've got something squared minus something squared, and then factoring according to my difference of squares rule, I get x squared plus 1 times x squared minus 1. Alright, notice this sum of squares, I'll call this factor here, sum of squares is always prime. So I cannot reduce it. But notice x squared minus 1 is also a difference of squares, is it not? So what I can do is here in this problem, apply my difference of squares pattern twice. Don't forget to carry down your prime factors into your final answer. X squared minus 1, well, of course, that's x plus 1 times x minus 1. So here is my final completely factored answer for the expression. Let me get it all in the frame here. Can't seem to get this quite in the frame. Let's see if I get. Here we go. The completely factored form of x to the fourth minus 1 is indicated below, right? X squared plus 1 times x plus 1 times x minus 1. Be sure your final answer has all the prime factors that should be included. Let's try another one. Factor a to the fourth minus 81. Alright, well, I'll bypass the training wheels and I'll rewrite this as a squared plus 9 times a squared minus 9 as before. And this, again, this sum of squares is prime. Sum of squares is always prime. So what I'm going to do is I'm going to carry that factor down to my final answer. And this is a difference of squares also. A squared minus 9 is indeed equivalent to a plus 3 times a minus 3. Is it not? Alright. So there's my completely factored form for that given binomial. Alright, things get a little more complicated in problems like this. If I ask you to factor, well, factor means factor completely. Two x to the fourth minus 32y. Alright, how am I going to factor this? Well, always look for GCF first in any factoring problem. And I can easily see I have a GCF here of 2y. I can factor out a 2y from this expression, and I'll get 2y factoring out the GCF times the remaining factor, x to the fourth minus 16, right? Of course, this is now this x to the fourth minus 16 is a difference of squares. I usually abbreviate that DOS. So I can rewrite this binomial factor as x squared plus 4 times x squared minus 4. Alright, so far I've got 2y times x squared plus 4 times x squared minus 4. Well, I think you see where we're headed here. X squared plus 4 is a sum of squares, always prime. Can't be reduced. So what I'm going to do is carry those two factors down to my final response. And of course, x squared minus 4 is a difference of squares. And I could rewrite that as x, whoops, not x squared, x plus 2 times x minus 2. Alright, so if I ask you to factor this expression completely, 2x to the fourth minus 32y, here is my final response. List all the possible prime factors. Now again, these are all being multiplied, so you can reorder these individual parentheses any way you like, as long as you include them all uniquely in your final answer. I want to do 3 problems in the homework list before we end this lecture. This one's number 13 on page 480. I believe it's in your homework list. For this section, if I ask you to factor 144 minus c squared. Now don't panic if you don't have a variable expression first in a given binomial. Of course, we can recognize 144 as the square of 12, can we not? So I suppose you don't have to, but I'm going to rewrite 144 as 12 squared. So if I've got 12 squared minus c squared, of course I've got a difference of squares. And according to the pattern, which we should have memorized for test time, it's going to be 12 plus c times 12 minus c. So that's the final return for that problem. Next one I want to look at is number 42. This is on page 481. 3ac to the fourth minus 243a. And we are asked to factor. Factor means to break it down into a product of irreducible polynomials. In other words, factor it in, break it up into factors that cannot be factored any further. Alright, look for GCF. I suppose there's always a GCF of 1, there's always a GCF of minus 1. Those usually aren't very helpful to factor out. Well, let's see, 3ac to the fourth minus 243a. What's the GCF in this binomial? I think the GCF is 3a. I think you'll agree you can factor a 3a out from both terms in that difference. Right, so if I factor out a 3a, I'm left with c to the fourth minus, well, 243. If I take out a 3, what's left? An 81, isn't it? So I end up with 3a times c to the fourth minus 81. Well, of course, c to the fourth, I can view that as a square. 81, that's 9 squared, is it not? So I can rewrite this as 3a times c squared plus 9 times c squared minus 9. And again, the sum of squares is prime. 3a, of course, can't be factored further, so I'll carry those factors down. And of course, c squared minus 9 is equivalent to c plus 3 times c minus 3. So this equals this in factored form. I've broken down that somewhat complicated binomial into a product of these factors listed in my answer. Okay? One more today. Let me get a fresh screen here. This one is number 85 on your homework list on page 481. 81, c to the fourth d to the fourth minus 16 t to the fourth. Somewhat nasty looking binomial. Well, I'll see that my coefficients are all perfect squares. 81 is the square of 9, 16 is the square of 4, and all the exponents in this binomial expression are multiples of 2. So it makes me think I can apply my difference of squares formula. So I'll rewrite this expression as 9c squared d squared plus 4t squared times 9c squared d squared minus 4t squared. Alright, convince yourself. If I view this as a difference of squares, if I multiply these two first terms, I do indeed get 81 c to the fourth d to the fourth. And if I multiply these two last terms, I do indeed get a negative 16 t to the fourth. Alright, the first binomial in this expression is prime. I know that because it's a sum of squares. Remember, a sum of squares is always prime. In order to break it down, you need a difference of squares, and I'll call that DOS. So to completely factor it, to break it down as far as I can, let's see, 9c squared d squared minus 4t squared, I can rewrite that as 3cd plus 2t times 3cd minus 2t. Alright, so all these factors here are prime. They're irreducible. That means I cannot factor any of these factors any further. So I claim the given binomial in factored form is the answer that I've boxed below. Okay? Alright, we're reaching the 19-minute point. We've done about 5 or 6 of these examples. By the way, the textbook talks about sum and difference of cubes, but we're not going to talk about sum or difference of cubes in this course. That's typically a topic left for pre-calculus. So I've just assigned the difference of squares type problems in this section. Alright, so this ends section 5.7, difference of squares.